Hi, everybody. Welcome back to Dr. Richard Edward Blyle's Chemical Principles for people who don't like homework. We're going to do something a little unusual today. We're going to extend the class by a factor of 3, and all we're going to talk about is hydrogen bonding. That's a joke. Don't turn me off just yet. I'm just kidding. We're getting close to the end. I was talking with my live student, Kim, about the syllabus. Looks like we have, after today, 3 more lectures. 3, what did we decide on, Kim? 3 or 4? Before special topics. How many?
3.
3 before special topics. It's all supposed to be nuclear chemistry. What I'm kind of doing at this point now, nuclear chemistry does not fall in the realm of traditional chemistry. It's a very different discipline, probably closer to related to physics than chemistry, but it's an important topic, so we are going to talk about it for at least 2 or 3 days. We have 2 special topics on the syllabus, so we can extend the class by a couple days if need be. What I'm kind of doing now, we're supposed to be talking about electrochemistry, but we're kind of far ahead on electrochemistry, so I'm cleaning up. There's some things that we have not discussed yet that I find important. And we're just kind of going through topics that we've not covered thoroughly enough or have not touched on yet. Such as last time when we talked about osmosis and diffusion. I don't remember talking about those, so we covered those. Because we're not doing homework, we're not really, bound to the order of things. So today we're going to talk about acids and bases, a very, very important topic, especially to physiological chemistry. And we're going to discover a few things we may not have known before. So it should be kind of fun. We'll be doing a lot of math today. So I hope you are comfortable with logarithms and powers. We're going to be talking about those. And I'll teach you what those mean and all that kind of stuff. Don't worry about it if you're not just yet comfortable with those things, because hopefully by the end of the lecture today, you will be. Okay, we are not transmitting, so we need to do that, and then we need to do that, and then we need to do that, and then we need to do that. And there we go, acids and bases. All right. Let's start off with some definitions. There are actually 3 definitions of acids and bases. Each one of them encompasses the previous, but expands the definition a little bit. So, the most basic definition of acids and bases are, is it Arrhenius? Yeah, it is. Are the Arrhenius. Acids and bases. It's the same Arrhenius that we saw in kinetics, the Arrhenius equation. By definition, an Arrhenius acid will dissociate to give us the hydronium ion. Here, A is not an actual anion. I'm using it as a generic anion because every acid will have an anion associated with it. So it could be chloride, could be fluoride, could be sulfate, could be a polyatomic ion, could be nitrate, acetate, could be anything. This is the hydronium ion. it is okay. Let's talk a little bit about your book, because your author probably does not write the hydronium ion in this fashion. Most books will write this like this. Because acids and bases occur. We're talking about aqueous chemistry. We're talking about water chemistry. The hydronium ion H plus does not really float around in solution freely. It actually associates itself with water. So your book will write the hydronium ion this way. Well, that's a lie too. So when I write H plus, it's a lie, but H3O plus is a lie as well. There's been research, and the reason it's a lie is because hydronium does not really associate itself with just one water. There has been research that has suggested that hydronium typically associates itself with 4 waters, which means that the hydronium ion is most appropriately written as H9O4 plus. That just complicates things. Honestly, it's a ridiculous complication. It's really H3O plus is really no more real, is no more realistic than H plus. So in your book, whenever they write H3O plus, just understand that when I write H plus, it means the same thing. It's some sort of a hydronium ion species. Should it be H plus, H3O plus, H5O2 plus, H7O3 plus? It could be any of those things. Actually, it's a combination of all of them if you want to know the truth. So I leave the water out just because I feel like the water is a complicating factor. But keep in mind, when I write H plus, here's your water. That's what AQ means. Aqueous means in water, specifically in water. So yes, I'm including water, just not explicitly, the way your author probably does. So an acid is any species that dissociates to give us the hydronium ion. A base, then, we're going to go with this. B is not boron. It's a generic. It's a generic cation is really what I'm representing here. A base is anything that dissociates to give us a hydroxide ion. Okay, pretty simple definition. Acids dissociate to give us the hydronium ion. Bases dissociate to give us the hydroxide ion. Before we move on to the second definition, I want to talk a little bit about acid-base neutralization. When we talk about neutralization, we're talking about acids and bases reacting together. And by the way, acids get a bad name. People are afraid of acid burns. In reality, base burns are just as bad, if not worse, than acid burns. They're bad too. So why we are not afraid of base burns, I have no idea. As a matter of fact, sodium hydroxide, one of the most common bases used in labs, sodium hydroxide is also used to strip away the flesh from the bones of skeletons, like yours. So bases can be very nasty as well. When I was a kid and I decided I wanted to become a chemist, this was around, well, this was middle school. We're talking around seventh grade, about 12, 13 years old. That was when I decided I wanted to go into chemistry. And I decided unrealistically at that time that everything that I learned in chemistry, I'm going to write on an index card. And I used to have a stack of index cards until I realized that there's really just too much to put on index cards. The very first index card that I ever wrote was if you react an acid with a base, you form salt and water. When you react an acid with a base, you form a salt and water. Two peanuts are walking down the road, and one is salted. Let's use the most obvious example of this. So for example, suppose we have hydrochloric acid. Now, when you're naming acids, it's a little bit different than naming regular ionic compounds. To name a simple acid, it's always hydro in first. So you start with hydro. That's what we use as the name of the cation. Hydro. Then you name the anion, but instead of naming it with the IDE ending, so it's not hydrogen chloride, you change the ending to IDE acid, IC acid. So instead of hydrogen chloride, it becomes hydrochloric acid. You always have to add that word acid on there. Hydrochloric acid. Bases are named as normal. So we react sodium hydroxide with hydrochloric acid with sodium hydroxide, which is just, you name the cation first, sodium. And then the name of the OH anion, it's a polyatomic ion. It's one of the ones I asked you to memorize. I'm sure I put it on the list. If not, it definitely needs to be there. It's a hydroxide. When you react this, it becomes something, it's really no different than a double replacement. Remember the double replacement where you take the cation from one salt and put it with the anion of the other. Then you take the anion of the first salt and put it with a cation of the other, and you get two new compounds. Well, this is the same thing. We're going to take the anion of the first one and react it with the cation of the first one and react it with the anion of the other. Here comes my cat. HOH. I've written this in a strange way. How many hydrogens are there? You don't have to turn on your microphone. Just hold up your fingers and make it clean. How many hydrogens? 7 hydrogens. How many hydrogens do you see in this compound here? You have a hydrogen on this. How many? You have a hydrogen on this side. You have a hydrogen on that side. 1 + 1 equals. There you go. Well, look, we have 2 hydrogens, 1 oxygen. Normally, the way that we would write 2 hydrogens would be like this. There's your water. Okay? So the water is formed from the hydronium ion and the hydroxide ion. We did talk about traditional chemical reactions in total ionic equations. In total ionic equations, recall, you take the salts, you take the ionic compounds and you dissociate them into the cations and the anions that you would actually have present in water. They do not stay together. They're ionic compounds. They dissociate. So we can do that here. Hydrochloric acid will dissociate to give us hydronium ions. Sodium hydroxide will dissociate to give us hydroxide ions. And of course, we get the chloride and the sodium. We're still going to form H2O. We have our total ionic equation. But remember, we talked about the difference between a total ionic equation and a net ionic equation. In the net ionic equation, we remove the spectator ions. Now, if you have a small spectator ion, then you have a spectator taut. The spectator ions are like the spectators in a sports event. When you have a stadium full of spectators watching the chess game that's going on in the middle of the field, and why don't we watch chess games that way? The spectators aren't really participating. They're watching, they're cheering, but they're not really playing the game. They're just spectators. They're enjoying their life. They don't change anything. I mean, you can say, well, yes, the players can feel the vibes and yada, 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 but they don't really change the game. So a spectator ion does not change in a chemical reaction. It is exactly the same in the reactants as it is in the products. So let's identify our spectator ions in this reaction. Is hydronium a spectator ion? Well, no, because it's the hydronium ion as a reactant. It's part of water as a product. That is not a spectator ion. But here we have chloride in the reactant side and chloride in the product side. It doesn't change. It's in its ionic form in both sides. It's aqueous in both sides. That is a spectator ion. Keep going. Sodium. We have sodium on the reactant side, sodium on the product side, both of them +1. The charge doesn't change. They're both aqueous. That doesn't change. This is a spectator ion as well. This is kind of a review because we have talked about this before. The hydroxide in the reactant side, we don't have hydroxide in the product side. The hydroxide has been taken up by the water. So we can write down the total ionic equation by removing the spectator ions, or the small spectator ions, which are, I already told that joke. So the net ionic equation is this. And we're going to come back to this reaction a little bit later. So anytime we have an acid and a base, what we're really doing, all an acid-base neutralization reaction is, it's the reaction of the hydronium ion from the acid with the hydroxide ion and the base to form water. We're going to come back to this reaction in a bit, but we started defining acids and bases. The first definition is the Arrhenius acid-base definition. Let's talk about I feel like I'm getting these backwards. I feel like the names may not be correct. Make you a deal. If your book has a different name for these, it'll cover them. But if your book uses a different name, your book is probably correct. But let's talk about Lewis. No, it's not Lewis. We're going to go with Lewis. The Lewis acid-base definition. This is we're just going to cover two because, like I say, I'm forgetting the name of one of them, and I get the feeling that I'm off. Oh, no, that's it. This is the Bronsted-Lowry acid base. Sorry about that. Bronsted-Lowry. Acid base definition. Now we'll cover Lewis bases as well. The Bronsted-Lowry definition begins the exact same way that the Arrhenius acid base. So if you have an acid, the acid will dissociate to give us hydronium ions. This is no different than Arrhenius. But if it's no different, why is it a separate definition? Well, it's the base that's different. It's all about that base. Sorry, that's a reference to the song. It's all about that base. The base in a Bronsted-Lowry base, the Bronsted-Lowry base does not have the hydroxide, but a Bronsted-Lowry base will absorb the hydronium ion to leave a hydroxide. All right. So a Bronsted-Lowry base also forms hydroxide ions. But it forms hydroxide ions by absorbing the hydronium ion, not by releasing the hydroxide. All right. So it absorbs a hydronium ion, which will leave behind a hydroxide. You already have an example. Well, we can use the same example for the acid. HCl dissociates to give H plus Cl minus. We can use a different acid if we want. Let's use a different acid. So, for example, nitric acid. Oops, there's no. Nitric acid will dissociate. Actually, nitric acid is a strong acid. Remember I told you in an equilibrium, what happens at equilibrium is the rate of the forward reaction equals the rate of the reverse reaction. If the rates are equal, the concentration of anything is not changing. And that's what happens in weak acids and bases. This is actually HCl is a strong acid as well. In a strong acid, we consider strong acids to be one way. So a strong acid will not be in equilibrium. It'll just dissociate and be done. Is there any reverse reaction at all? Yes, there is, but it's negligible. Again, it's a strong acid. It doesn't really want that hydronium back. Weak acids do. All organic acids are weak. But it dissociates to give us the hydronium ion once again, and we get the nitrate anion. That's one of the anions I asked you to memorize. And I love nitrates because they're cheaper than day rates. So we get the nitrate anion. As an example of a Bronsted-Lowry base, let's look at ammonia. Now, this is ammonia, and the concept of anhydrous ammonia, not really right. Anhydrous means without water. But at normal temperatures, ammonia, it's a vapor. It dissociates into vapor. So to have an anhydrous ammonia, really what they're talking about there is highly concentrated ammonia. It's a solution of ammonia. It is in water. It's just very, very concentrated. And if you remember the Lewis dot structure of ammonia, it has this lone pair of electrons on it. This will react with water. This is a weak base, so it is in equilibrium, to form the ammonium ion. Notice, now remember, all of these definitions are backwards compatible. So when in Bronsted-Lowry base reacts with water, it leaves behind the hydroxide. So it is backwards compatible with the Arrhenius definition. It's just that this is not an ionic base where it dissociates to give hydroxide. It actually absorbs the hydronium. It absorbs the hydronium to leave a hydroxide behind. What's really happening here? What's really happening is we are forming a new bond. This ammonia is going to form a bond with hydrogen. Now, every bond involves two and only exactly two electrons. But normally, when we form a covalent bond, one electron comes from one atom, the other electron comes from the other atom, and that's where the two electrons come from. Okay? That's a chemical bond. That's a covalent bond. One donates one electron, the other donates the other electron. You get two electrons being shared. This is a special kind of bond because what's happening is the two electrons in the nitrogen are being used to form this bond. When you do a Lewis dot structure of a polyatomic ion like ammonia, by convention, you put it in square brackets with the charge above it. This becomes a +1 charge because nitrogen originally started with two electrons that it had all to itself. All of a sudden, it's donating one to the hydrogen to form actually it's donating both to the hydrogen. So now these two electrons are being shared by two atoms. In essence, it kind of lost custody of one of those electrons. It's being shared. Those two electrons are being shared. So if you kind of think about it, two electrons, two atoms, each atom is kind of one. So it loses one of those electrons by sharing. And the electrons that were originally, we cannot violate the octet rule. So if we take hydrogen away from water, these two electrons are going to go to the oxygen. So instead of one lone pair, oxygen now has, instead of two lone pairs, oxygen now has three lone pairs. And because it was sharing two electrons, now those two electrons both belong exclusively to oxygen. So just like nitrogen kind of loses one electron in this exchange, water kind of gains one electron. Now it has exclusive ownership of one of those electrons that was originally shared. So we get the negative. This is still a covalent bond. Okay, we are forming a bond between two elements, and in doing so, well, we're still sharing two electrons. It's still a covalent bond, but the difference, this is a little bit different, and this is an important difference. Most covalent bonds, like I said, one electron from both species. This time, both electrons come from the same atom. It's a lone pair that's being shared. Both electrons are coming from the same element in that covalent bond. That makes it a very special covalent bond that we call a coordinate covalent bond. It's just like a covalent bond, two electrons being shared between two atoms. But this time, the source of those two electrons are both from the same element. That is a coordinate covalent bond, and it's not just water chemistry. It turns out coordinate covalent bonds, you see them in other reactions as well. For example, if you have an older home, they used to use heavy metals as pigments in paints. Lead, mercury. That's because heavy metals tend to form very stable, so they last for years and years and years, decades. And they also are very colorful. Mercury oxide is a beautiful red color. You can get all kinds of different colors out of heavy metals. So they were used as pigments in paints. That's why if you have an older home like mine, this home was built in the 19th century, late 19th century. Actually, early 20th century, now that I think about it. It's about 100 years old. These paints probably have lead in them or mercury because those are very highly colored salts. Very hard to mitigate. No, actually, it's not hard to mitigate. It's easy to mitigate. It's very hard to remove. Very dangerous to try to remove paints that are old because if you get dust, you're breathing it, and that's going to get into your system. Lead, mercury, the heavy metals cause what we call heavy metal poisoning, which means that you're not just going to keel over and die, but your body can't get rid of heavy metals. So once heavy metals get in your body, they accumulate over a lifetime. If you ever played with mercury as a child, like I did, that mercury absorbed through your skin, through my skin, and it is still in my body today. That mercury haunts me to this day. As you accumulate mercury over the years, eventually it's going to reach a concentration where you start to see the effects of the heavy metal poisoning, such as shaking, it's called the mercury tremors, hair loss, which obviously that's not a problem for me, insanity, which is my all-time favorite side effect of heavy metal poisoning, and eventually death. And once you're dead, there's not much we can do for you. Mad as a hatter is an expression. Hatters actually became quite insane because they worked in enclosed little rooms with poor ventilation, and they used mercury in the manufacture of their hats. So over the years, they accumulated heavy metals until they went insane. They literally went insane. Some people think that Edgar Allan Poe suffered from heavy metal poisoning, which is why his writing was so dark. But today we can treat heavy metals. This is something that developed in the 70s, so it's not a new treatment. It's called chelation therapy. And do not confuse chelation therapy with the medical chelation therapy with the charlatan chelation therapy. My apologies if there's a charlatan watching this. If you see an advertisement saying chelation therapy can cure everything and I can handle it, I'm not a medical doctor, but I'll give you chelation therapy. No, it's nonsense. What's really happening, so this is kind of a cool thing. And it kind of leads to the next. What's really happening is this. Chelation therapy, your body cannot get rid of heavy metals, but it is beautifully designed to get rid of organic garbage. So if you have a heavy metal, chelation therapy, any chelating agent is designed for one specific metal, all right, like ethylene diamine. My first serious chemical burn was ethylene diamine. It taught me that I was not being careful enough, and it bit me. It's a beautiful organic compound. Lewis dot structure. It has two nitrogens, I'm sorry, connected by an ethyl group. Like this. Now, chelating agents will only bond to one specific metal. That's why generic chelation therapy is a waste of time and money. You may remove some toxins, but it's not going to remove all the toxins, and it may be removing good metals. For example, wintergreen forms these structures. Oil of wintergreen forms them with iron. Do you want to take iron out of your body? No. So be a little careful. Don't go to a charlatan for chelation therapy. And what happens is you have a cation. It's a little hard to draw in 2 dimensions. So if you imagine a cation with, come on, erase. There you go. I'm going to draw an imaginary plane. So that plane is a plane with a metal in the middle. I'm going to represent ethylene diamine like this. Okay. So this is just a shorthand representation of ethylene diamine. And what happens, boy, am I glad we're talking about this. This is such a cool concept. Not 1, not 2, but 3 ethylene diamines will react. Well, yeah, they'll react. We'll say that. With a metal like this, it will literally surround that metal to form what we call a complex. Poor little sad metal, because life is complex for it. Your body cannot get rid of this metal, this lead or mercury or whatever ethylene diamine bonds to. It cannot get rid of it. But your body can get rid of ethylene diamine. So what happens is your body finds this gamush of ethylene diamines with a heavy metal hidden on the inside. It doesn't see the heavy metal, but it sees all of these ethylene diamines, and it says, that's no use to us. Why are we keeping this? And it takes those ethylene diamines and gets rid of them. And as it drags those ethylene diamines out of your body, it takes that lead or mercury with it. This is chelation therapy. And it's all done with coordinate covalent bonds, which leads us to our final definition of acids and bases that has nothing to do with hydroniums or hydroxides. We're going to define this backwards. A Lewis base is a lone pair donor to form coordinate covalent bonds. Therefore, a Lewis acid is a lone pair acceptor. Now, I promised you that all of these definitions are backwards compatible. The Lewis definition does not even require water. Does not require water. It's much more generally applicable than Bronsted-Lowry or Arrhenius acids and bases. But I want you to notice this. Here we have the Bronsted-Lowry acids and bases. Look, the Bronsted-Lowry base is a lone pair donor. The Lewis acid is the lone pair acceptor. So the Lewis definition of acids and bases is backwards compatible with the Bronsted-Lowry definition. And as we mentioned before, the Bronsted-Lowry definition is backwards compatible to the Arrhenius definition. Okay, it is 10:41. I'm going to talk for 4 more minutes before we take our break, or a few more minutes before we take our break. So you will get your full 5-minute break. But I want to go back to this reaction. Sorry. As you recall, this was the net ionic equation for the Arrhenius acid-base reaction. Now, this is an equilibrium, and remember, we are allowed to reverse the reactants and the products because it's a two-way reaction. So I could just as easily write this. This is a very important reaction. Okay, this is called autodissociation. And no, autodissociation does not mean that you parked in the wrong part of town. It means that in water, water is constantly dissociating, whether there's an acid or a base or not. It's an equilibrium. Water is always dissociating. Now, we talked about how to write an equilibrium constant expression, and I told you this. I told you this. Sometimes we leave things out. For example, earlier I said, look, you always leave out the more condensed states. So if you have an equilibrium about something that's subliming, for example, you don't write the solid down, you just write the gas. Unless you're Mick Jagger, in which case it's a gas, gas, gas. The other thing that you always leave out is water. You always leave water out of the equilibrium constant expression, because anytime you're in an aqueous reaction, the concentration of water does not change enough to bother to put it in. The concentration of water is kind of a constant. So we can write this equilibrium constant expression, and it is specific to water. So we write Kw, and it's always products over reactants. And we get this equilibrium constant expression. And Kw is a real constant. It is measurable. Chemists have figured it out. Kw is always, always, always equal to 1 times 10 to the negative 14th. That is only for water. Okay, this will be where we pick up after the break. But, and this is a big hairy but, it is 10:45. Let's take 5 minutes. Kim, I will see you back here at 10:50. Thank you much.
Okay.
All right. So we last time before break, we ended with this simple little equation. Kw is equal to the hydronium and hydroxide ion concentrations. That means, and this is kind of an interesting thing, there's always, in water solutions, there is always hydronium ions. There are always hydroxide ions. An acidic solution is not an acid because it only has hydronium ions. What makes it acidic is that it has a higher concentration of hydronium ions than hydroxide. But there's always going to be at least a little bit of hydroxide ions in there. Always, always, always. Because this equation must always, always, always be true for water solutions. As we look at Kw, some of you may recognize this portion. And you may recognize it from the pH scale. The pH scale runs from 0 to 14. Do you ever wonder why? Do you ever wonder why the pH scale is backwards? Lower pH means higher acidity. Why is it backwards? Let's talk about logs. Let's talk about P. What is P? When we talk about P, we're not talking about what I just did during break. Okay, if that joke offends you, please feel free to contact me. I will refund your money. P is a mathematical definition. The P of any number, X, is defined as the negative log, and this is base 10 log of that number. All right, so if you look on your calculator, you will see mine is very strange because mine is a second function. But if you look on your calculator, you're going to see an log key. That's what this is. It is right next to an ln key. ln is natural log. That is not what we're going to use for these calculations. For these calculations, it's base 10. And the definition, there's not a rhyme or reason. This is just a definition. The p-value of any number x is equal to the negative, or the negative sign here, log of that number. We do this because it makes it easier to deal with exceptionally small numbers. Now, if in your calculator you put in 1 times 10 to the negative 14th and press log, you will get a negative number. But then you change that negative number to a positive number because of this negative right here. So pKw is simply equal to 14. And 14 is so much easier to write than 1.0 times 10 to the negative 14th. All right? That's a definition. That's just a definition. While we're talking about definitions, let's talk about this. Yours, now mine is backwards, but probably your second function. For me, it's the first function. This probably second function to your log key is 10 to the x. That every mathematical function has an anti-function. The anti-function of log is called the anti-log. I've been laughed at for calling it this, but the anti-log of any number, if we want kW back, it is 10 raised to the value of this. Or, okay, so you have to change it. So if you take 14, change it to a negative sign and press 10 to the power, you will get back 1.0 times 10 to the negative 14th. Let's do a real quick calculation using this. Now, I told you this. I told you this already. In an aqueous solution, anything, what you're drinking, that's water. It's mostly water. It has flavorings and things like that, but it's mostly water. Hopefully this water is neutral. You don't want it too acidic, and you certainly don't want it too alkaline. Alkaline is another word for basic. You want it kind of somewhere in the middle. You want it neutral. Well, if it's completely neutral, I'm gonna emphasize this: neutral only. Your hydronium ion concentration equals your hydroxide ion concentration. Your water is probably not neutral. The odds that it's exactly neutral are almost zero. But a little bit of acidic, a little bit of basic, that's fine. It's actually, you can get relatively acidic, a little acidic solution is fine, a little alkaline. The water you're drinking is probably slightly acidic because carbon dioxide dissolves in water to form carbonic acid. We've talked about that before. So yeah, tap water to standing water, eventually it becomes slightly acidic. If you've ever drunk boiled water, if you watch really carefully as water boils, and I have a friend from India, and she only drinks hot water because in India, you learn. You boil the water before you drink it to make it safe. It's not as, it may not be true today. I'm sure that India has improved its water quality, but back then, we're talking 1980s, the water was not really consistent. So they would boil their water. And Indrani, my friend, got used to drinking boiled water, which to me just tastes awful. She likes the flavor. She doesn't like the flavor of water that has not been boiled. If you watch boiling water very carefully, you will notice that before you get the rolling boil, you get little bubbles that form and just dissipate. Get those tiny little bubbles. Those tiny little bubbles that come before boiling, those are carbon dioxide. That is carbon dioxide accumulating and leaving the water. As the carbon dioxide leaves the water, that means that any carbonic acid that the carbon dioxide formed is leaving is being converted back into plain water. That means that the pH, that means that the water is going closer to neutral. Instead of being slightly acidic, it becomes neutral. And acids have kind of a bitter flavor. If you've ever had seltzer water, that's just water with a lot of carbon dioxide in it, which means it has a lot of carbonic acid. It's a very bitter flavor. It's kind of hard to take, honestly. Some people like it, I don't. That's why soft drink companies, they like the fizzing. That's their gimmick. They want you to drink it because it's fun to drink because it fizzes. But now how do you deal with the bitter flavor of the carbonic acid? Well, you add tons of sugar. That's why when pop goes flat, unless it's a soda, when pop goes, sorry, it's reference to something happened to me. I think I told you that story. But when pop goes flat, The carbonic acid is gone because the carbon dioxide is gone. The bitter flavor is gone, but sugar is still in there. That's why flat pop tends to taste so sweet, because the bitter counter flavor is gone, but the sugar remains. So back to our calculation here. If the hydronium ion concentration is equal to the hydroxide ion concentration, then we can replace the hydroxide ion concentration with hydronium because it's the same. Three dots in a triangle like this is a mathematical symbol that means therefore. Therefore, for neutral only, for neutral water, the hydronium ion concentration, you can punch this in your calculator if you need proof, is 1 times 10 to the negative 7th moles per liter. Remember, square brackets mean mole per liter. It's molarity. Now, 1.0 times 10 to the negative 7th. You may or may not be recognizing this, but look. Our number here is the hydronium ion concentration, so we're going to call it pH. pH. H stands for hydronium ion concentration, specifically hydronium ion molarity. And we're still for neutral solutions only. You can punch this in your calculator if you like. For neutral solutions, pH equals 7. A lot of people know that the pH scale is a 14-point scale, from 0 to 14, but they do not understand why. This is why. Because Kw is 1 times 10 to the negative 14th. That's where that 14-point scale comes from. A lot of people know, but do not understand why. The lower the pH, the more acidic. Here's why. It's because in this definition, there is a negative sign. Oops. Go back. Go back. There you go. Because of that negative sign right there. The higher the concentration of the hydronium ion, the lower the pH will be. And that's why. It's because of that negative sign right there. That's why low pH is high acidity. Now, what a lot of people don't realize is that when we're talking about pH, what we are giving you in pH is it's a form of the exact concentration and molarity of hydronium ion concentrations. pH is an actual measure of hydronium ion concentrations. If you've ever measured pH, you can get pH meters if you have like a fish tank You probably have a pH meter, or they have little test strips that will tell you what the pH is. If you've ever done that, you're actually measuring the molarity of hydronium ion concentrations. That's all you're doing. Let's do another quick example. Scientists are freaks. They're absolute freaks. We do the weirdest stuff. You have no idea. I just made a major advance on a project that I'm working on, that I've been working on since the 70s. 35, 40, 45 years I've been working on this project. That's how our mind works. We ask a question and we're like a dog with a bone. We will not let it go. A biologist, many, many, many years ago, wanted to know what is in the stomach. So he needed a sample of stomach fluid from a live person. He wanted to know human stomach content. The live person he chose for this experiment was himself. And in order to get a sample of his stomach fluid, he took a metal test tube and he drilled holes in it. He put a sponge down in there and he tied a string to it. And guess what? Are you gagging yet? Because you should be. It was the old sword swallowing trick, only with a metal test tube. When he swallowed it, he took that string, pulled it back out again, somehow did not throw up. Maybe he did, I don't know. And he got his sample of stomach fluid. He discovered that the stomach fluid was HCl. Hydrochloric acid, that's what's in your stomach. And at a very high concentration, which you would expect it to be because it's trying to break down foodstuffs. And I say foodstuffs because I just always thought that was just a funny sounding word, foodstuffs. He discovered that the HCl, I'm making this number up, it was acidic. The pH of the HCl was around 1. Now, I don't know the exact number. I'm going to assume that he was feeling a little acidic that day after swallowing a test tube. I'm going to say, for this example, that the pH was 0.8. Very, very acidic. Probably more like 1.2, but we're going to go to a very acidic. For this demonstration, we're going to go to a very acidic number. Okay. What I want to know is the hydroxide ion concentration. This is a highly, highly acidic solution. Is there any hydroxide at all in there? Well, let's find out. If you go back and look at these equations, there's a couple of ways you can do this. First of all, well, let's use, I don't want to give you too many ways to do it because you're not going to practice anyway. Let's use this equation because this is an important equation and I think we should use it. So in order to use this equation, we need to find the hydronium ion concentration. How do you do that? Well, you find the hydronium ion concentration using this equation. So since pH is equal to negative log of the hydronium ion concentration, we can say that the hydronium ion concentration must be the anti-log of the negative pH. Okay, so we can move back and forth between molarity and pH. So feel free to play along to see if you get the same number that I do. Different calculators are different. I cannot tell you how to use yours. A lot of the modern calculators, actually you put in the log first. Mine, no, you put in the number and then you hit the 10 to the power. And this is a reasonable number, so I know that it is correct. I'm going to say it's pH 8.0. Actually, I'm just going to mess up sig figs. I should only have one sig fig here. I'm going to go with 3. Oops, I did that wrong. You should be getting 0.158, and that is moles per liter. Okay, so we have a very high concentration. Well, now we can use the equation. This very important equation, because it tells us about the nature of water in aqueous solution. It tells us about the nature of your body, of your drink, your cleaning solutions. We always know Kw. Now we know the hydronium ion concentration. What we do not know is the hydroxide ion concentration. Divide both sides by 0.158. Little bit of algebra here. And we get a hydroxide ion concentration of 6.33 times 10 to the negative 14th. The hydroxide ion concentration is not 0, but it is excessively small. It is point. Ready for this? 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 633. It is 633 with 14 zeros between it and the decimal point. It's exceptionally small. The hydronium ion concentration, 0.158. Very high. Now, by the way, just because you may see it, yes, there's also something called POH. Just like pH, it is the negative log of the hydroxide ion concentration. Your number may have rounding differences from mine, but it will be very close to 13.2. 13.2. So we can also talk about POH. And you may notice, by the way, if you add the pH, 0.8, to the POH, oops, 13, go back, there you go, 13.2, you'll notice that equals 14. I'm going to write that sideways here just because we can. It's a little, it's the result of the mathematics, basically. The pH plus POH is equal to pKw, or 14. pKw, not KW. So pH plus POH equals 14. So it's actually very easy if you're given the pH to find the POH. Then you can find hydroxide by doing the anti-log, and going backwards once again, and yada, yada, yada. It's all related. We went through this very quickly. Again, the point here is if you're helping your child with homework, I want you to have at least seen it. But here are the big takeaways from today. I want you to understand what acids and bases are. You don't have to worry about Lewis acids and bases. You don't even have to worry about the Bronsted-Lowry. Basically, an acid has hydronium ions, a base has hydroxide ions in excess. And that's the other thing I want you to understand. It's not that it's missing one. It's that an acid has hydronium in excess, and hydroxide has hydroxide. I'm sorry, bases have hydroxide in excess. Acids have hydronium in excess. Bases have hydroxide in excess. But there's always, always, always the other. I want you to understand that as well. We're talking about auto-dissociation of water. You don't have to worry about the term auto-dissociation. But when you talk about pH, which is a common, people often talk about pH, I want you to understand that when you give pH, you're giving the exact concentration of the hydronium ion in the water. Okay, that's what pH is. It's the hydronium ion concentration given as its p-value as opposed to the molarity. You will see P every once in a while. I see it several times a day. For example, any logarithmic scale uses P. I was looking at the lab results from medical labs that I had done. The last time I had medical labs done, which was 29 years ago. I'm saying that for my friend Kim because she's now very irritated with me. It had on there PNA. One of my results was PNA. What the heck is PNA? Well, P is negative log. Na is the atomic symbol for sodium. They were giving me my sodium ion concentration in my blood. And if I want to know the molarity, it's the anti-log of the negative PNA. So sometimes you will see these P numbers in other places. And now you know what it means. Now you know what P represents. And you know how to flip back and forth between the P number and the actual number. You now know why the pH scale is 14. You now know why neutral pH is 7. And you now know why the pH scale is inverse from the acidity. The lower the pH, the higher the acidity. We've covered all of that. This is all critical in physiological chemistry. If you've ever hyperventilated, Kim, have you ever hyperventilated?
Yes.
What happens? Physiologically, what starts happening? How did you feel?
Tingling.
Get tingling in your fingers. Yeah. Anything else?
I feel like you're going to pass out.
Start feeling lightheaded, like you'll pass out. Kim, if you kept hyperventilating, eventually you would get cramping, especially in your hands. That's all happening because you're losing carbon dioxide. As you lose carbon dioxide, the carbonic acid in your blood, in your body, is dropping. That concentration is dropping. And as the concentration drops, the hydronium ion concentration drops. As the hydronium ion concentration drops, your pH starts going up. It's called alkalosis. Your body must maintain a proper pH because if it does not, the proteins cannot function. Your proteins begin to denature. which means they lose their structure and they can't work. And that's why you start feeling lightheaded. That's why you start cramping up, feeling tingling, all because of pH. And that's what we covered today. Any questions before we go?
No.
Kim, thank you so much for joining us. Don't be late for your next class. I am out of here.